Hello, welcome to a new video on metric spaces. Here we define the concept which is called the nowhere dense subset of a metric space. When we can say that a subset of a metric space is nowhere dense, see, we consider a subset A of a metric space X. Let A be a subset of a metric space X, and we say that it is nowhere dense if closure of A has empty interior. So if closure of A has empty interior, that is, if interior of closure of A is equal to the null set. So the condition for saying that a subset A of a metric space X is nowhere dense is that you take closure of A. If closure of A has empty interior, then we say that it is nowhere dense. So in that sense, if you have a closure of A that contains, if closure of A contains in its interior some open sets or some open balls, then we cannot say that its interior is empty. So in that sense, we can say that every open sets are not nowhere dense. That means open sets are not nowhere dense. They are non-examples. So if you take an open set, then it is not nowhere dense. So for an example of nowhere dense set, you can consider the sequence 1 by n. The sequence 1 by n, it is nowhere dense. The sequence 1 by n as a subset of R is nowhere dense. So next one, you take the set of rational numbers Q. See, Q is the set of rational numbers. Then when we take its closure of Q equal to R, and that has no empty, its interior is not empty. It's full of elements. Actually, its interior is not empty. It contains infinitely many open sets. Interior of R contains what's actually its interior. Interior of R is R itself. Interior of the real line is R itself. So it contains infinitely many open sets, and so it is not nowhere dense. Which set that subset of R, that is the set of rationals Q. The subset Q is not nowhere dense. Therefore, so it's an important example. Next, we consider more examples of the more subsets of the real line. We consider more examples, and we one by one we take example subsets of the real line. Any finite set, you consider any finite set, any finite subset of R, it's nowhere dense. Every finite subset of R is nowhere dense. And the sequence 1 by n, where n varies from 1 to infinity, we have mentioned that it is nowhere dense. This sequence is nowhere dense. And the set of integers is also nowhere dense. When we consider the integers, we can say that it is nowhere dense. The set of all integers is, or any subset of integers, it's also nowhere dense, because it can be finite or infinite. See, it's nowhere dense. But the set of rationals is not nowhere dense here, due to the fact that its interior of the closure of a set of rationals. You take the closure of the set of rationals, its interior is not empty. So it is not nowhere dense. And then we consider, after that, let's consider the plane, and that's R2. We can consider the plane. Then in a plane, every finite subset of a plane is also nowhere dense. The points whose coordinates are integers, you consider all the points whose coordinates x and y coordinates are all integers. If the x and y coordinates are integers, that means lattice points. We take the lattice points of the on the plane. The set of all those points and its subsets are nowhere dense. Any finite collection, also every finite collection of lines is nowhere dense. Every finite collection of lines is nowhere dense. A circle, you take a circle, it's also nowhere dense. See, these are examples of nowhere dense sets. Some non-examples are also given. Next, we have a idea. We have an idea to define, and that is the first and second category. Here we are going to categorize the metric spaces. We have a categorization of metric spaces. A metric space or its subspace, see, a metric space X or its subspace A, its subspace, and that is a union of, that can be written as the, expressed as a union of a countable family, countable collection of nowhere dense sets. It's called, if that happens, if we can express, if we can write a metric space or its subspace as a as the union of a countable family of nowhere dense sets, we can say that that metric space belongs to the first category. Then we say that the metric space is in the first category. If it is not possible to write it as to write it as the union of a countable family of nowhere dense sets, we say that it belongs to the second category. So this gives us the categorization of metric spaces. Next, we have to discuss a lemma. In this lemma, it links, or it tells about the subset A of a metric space X, and when it can be nowhere dense, or a characterization. It gives us a characterization of a subset A of a metric space X that is nowhere dense. So it's a characterization of nowhere dense subsets of a metric space. A subset, let's read that lemma. A subset A of a metric space X is nowhere dense in X if and only if each non-empty open set in X. So if and only if each non-empty open set in X contains an open ball. Each non-empty open set in X contains an open ball whose closure is disjoint from A, or which, or we can say that in another way, we can say that its closure avoids the set, the subset A. See, if each non-empty, you take any non-empty, every non-empty, any non-empty open set in X, and then its closure, if its closure avoids the set A, the subset A. In such a situation, we can say that the subset A is nowhere dense. So if this condition is, if this is true, then we get that A is a nowhere dense subset, and if the nowhere dense subset, if A is a nowhere dense subset of the metric space X, then we can show that this condition is satisfied by that, by every non-empty open set. See, every non-empty open subset in X. Yeah, it's the property. It comes as the property of every non-empty open subset. Yeah. Thus, every non-empty open subset, and here now in this lemma we are linking an arbitrary non-empty open subset of X and a nowhere dense set. See, the two types of subsets are taken here. A is a nowhere dense subset of X. A is a nowhere dense subset of X, and then the second thing is non-empty open subset. See, non-empty open subset of the same metric space. See, we are comparing these two. So, and we establish an if and only if statement, and that if and only if statement becomes a characterization of nowhere dense subset of X. We can now come to the proof. So first we suppose that A is a nowhere dense subset of X. See, we take a nowhere dense, A is a nowhere dense subset of X. And let's also take, so we have told you that we are considering two subsets of, we are comparing two subsets of X. First A is a which is taken as a nowhere dense subset, and then we have to consider an arbitrarily chosen open set. And so the second thing we have to take, let O be an arbitrarily chosen an open subset of X, OB, and we name it, we arbitrarily choose an open subset of X, and that is named O. Since closure is closed, see, is nowhere dense, and since okay, it's very general thing. We know that closure of A, we consider closure of A, then closure of A is then closed. It is clear by the definition. Closure of A is closed. Since we have the set closure A is a closed set and O is an open set. So O minus O, we are removing all the elements or the members of closure A from O. Since closure A is closed, O minus O is already open. O minus closure A will still be open. So open set, from the open set we are removing members of a closed set. So O minus closure A is open. Open. Where is it open? It's open. It's an open subset of X. It's open in X. So next we choose a member of that set, that open set O minus closure A. So this is not capital X. Let the small x be an element of O minus other deleted from the set O from the set O from which closure A is deleted. Then we can find an open ball because it is open, because of the fact that the set O bar closure is this set is open. Because it is open, and since X belongs to that set, we can find an open ball. We can find an open ball Bx epsilon. Where epsilon is some positive quantity. We can find an open ball Bx which is centered at X, at the point X, and having radius epsilon, Bx epsilon, which is well contained in that open set. And that comes from the property of open sets. And so it is clear that the intersection of that open ball, because it belongs to the open ball is chosen from the set O from which closure A is removed. Therefore intersection of the open ball and closure A, because it does not share, closure A does not share any point with the open ball, because already all the members of all elements of closure A are removed from the open set O from that set. Therefore intersection of Bx epsilon and closure A equal to the null set. So no element is shared by these two sets. Next we okay, therefore this implies that Bx epsilon intersection A is also, it's because closure A contains A and all the limit points of A. Okay, therefore closure A well contains A, or A is a subset of closure of A. Therefore Bx epsilon intersection A is also still it's empty set. Why? It's because A is a subset of closure of A. We know that since A is a subset of closure of A, its intersection of the open ball with A also will be empty. Next we choose a new quantity delta, another positive quantity delta, which is the half of epsilon. The first quantity epsilon, half of epsilon, that is epsilon by 2. We choose delta equal to epsilon by 2 and consider the open ball Bx delta. So it will be Bx delta, and that has the center at X. X is the center of the new open ball. This is a new open ball Bx delta. So and its radius is half of the radius of the first open ball. So it is well contained in Bx epsilon. So Bx delta, and this Bx delta is a subset of Bx epsilon. It is very clear, and also since it is its radius is half, very small than the radius of the second ball is very less than the radius of the first ball. Its closure. See, you can think about the closure of Bx delta. It's a closed set. So that contains all its boundary points. Closure of Bx epsilon contains the boundary of the open ball having radius delta and center at X. It is then very well inside. It's a subset of Bx epsilon. That implies that see Bx delta intersection A is also, see Bx delta closure of Bx delta intersection A. It's because Bx epsilon intersection A is equal to the null set. It's empty. So since this is a subset of this open ball, and therefore this closure Bx delta intersection A is also equal to empty. and thus for each open therefore for each open set O in X, for arbitrarily chosen open for an arbitrarily chosen open set O in X, we can find an open ball. What is that open ball? See, that open ball is the second open ball chosen here, Bx delta. We have an open ball Bx delta, and that's actually taken from Bx epsilon. Yeah, and its closure is taken, and there exists an open ball Bx delta which is contained in O. Bx delta is contained in O, it's because it is contained in Bx delta is contained in Bx epsilon, and Bx epsilon is a subset of O. It is contained in O. It is contained in O, but its closure, so, and its closure of Bx delta is a closure of Bx delta, and then bar. It is a disjoint from, see, we get that it is disjoint, it's a subset of that, therefore it is disjoint from A. Yeah, it does not contain any point of what does this statement say? The last statement says that Bx delta, a closure of Bx delta has no point shared with A. Bx delta closure of Bx delta has no point shared with A, and this closure is the closure of an open ball. So this is the open ball which is mentioned here. Thus there exists an open ball Bx delta. Its closure does not have any point which is shared with A. That means the closure of this open ball completely avoids the set A. Okay, thus proof in one direction is now complete. Now to prove the conveys part, conversely we suppose that each see that last part that we have proved here will be assumed now, will be taken as an assumption. We assume that it is true. We assume that the following is true, that each non-empty open set in X centered contains an open set. Each non-empty open set in X contains an open ball. Actually, it contains an open ball. Each non-empty open set in X contains an open ball. That correction you can make here. It contains an open ball whose closure is disjoint from A, or whose closure avoids the set A, where A is whose closure avoids the set A. Then we have to show that where A is a subset of here. At this moment, we just think that we know what we know about A is that it's a subset of the metric space. A is a subset of the metric space X, and now we want to show that A is then nowhere dense. We have to show that by the end of this the river conveys part, we have to show that A is nowhere dense. So if possible, but in order to get that to prove that A is nowhere dense, we just think that its opposite is true. Then we will obtain the contradiction. So actually we want to show that A is nowhere dense, but you just think that for the time being you just think that it is not nowhere dense. If you can then proceeding with that, by thinking that A is not nowhere dense, if you can derive a contradiction, then you get that you have to correct that contradiction, and by that correction you will get that A is nowhere dense. So that's what we are going to do here. So if possible assume that A is not nowhere dense. See, A is not nowhere dense. That means closure of A is not equal to phi. That means closure of A is not empty. That means closure of A has interior of closure of A is contains some points. See, what does it mean? It means that interior of closure of A contains some points, or closure of A is not equal to phi. Okay, if closure of A is not equal to phi, of course you can choose an element. You can pick an element. You can select an element of closure of A because it is not equal to phi. It is not empty. So let small x be an interior point of we choose an interior point because it is not equal to phi. So let x be an interior point of closure of A, which it implies that that means there exists an open set. See, if x is a member of interior of closure of A, that means there exists an open set. then we can find an open set. There is an open set O which is contained in X. There is an open set which is contained in capital in the metric space X, and also which contains which contains X. See, then there is an open set O in X which is contained in capital X, but moreover that that contains, that open set contains a small x. The small x is contained in that open set. Open set contains small x, and also it is contained in closure of A. So that is contained in closure A, and that open set must be contained in closure A, or it is contained in the interior of closure A. And that also is correct. So every and so since it is open, in every element of O, C, and then since it is inside, it is contained in closure of A. Okay, we can think about that. Since that open ball, open set is contained in closure of A, then therefore every element of O, you can think about every element, each and every element of that open ball O. That each element is either a point of A, because closure of A contains all the elements of A and also all the limit points of A. We know that closure A can contain all elements of A and as well as all limit points of A. So and since O is contained in closure of A, and then every element of O must be either a point of O or a point of A. Every element, each member of O must be either a point of A or a limit point of A. Okay, it's either a point of A or it's a limit point of A. You have to consider both the situation, and thus every open ball in O. Therefore, every open ball in O contains a point of it contains a point of A, and which is that therefore it means that in both cases what happens, there we have two situations. See, every point of A it's can be either a point of A or a limit point of A. It's either a point of A or a limit point of A. In both the situation, whatever be the situation, in both cases, you can see that every open ball in what does it mean? And the meaning of the previous statement is that every open ball in you consider open balls in in O. Every open ball in O in the open set O, in the set O, that contains a point of A, because if that element, if the member, see, if an element of O, if it's suppose that it is a member of A, if it's a member of A, then that can be a member of an open ball. So therefore you take every open ball of O, open ball in O, then you can see that that open ball then contains some point, and that points will be is a member of O, and that member will be either a point of A or it's a limit point of A. In both situations you can see that it contains. If it's a point of A, then we can say that this is true. Then every chosen open ball contains a member of A. But suppose the second situation is true, that is it's a limit point of A. Suppose it's a limit point of A, because that point is a limit point of A, then that open ball must contain, since it's a limit point of A, and the same there must exist an open ball, or every open ball for every open ball, that open ball must contain some point of A other than, it's because other than this point, the point we are considering, which is under consideration, we have chosen a point C belonging to O. So that with respect to that point, you can say that if that point is a limit point of O, then some point, every open ball must contain some point of A. It must contain some point of A other than that limit point. Then only we can say that it's a limit point of A. That in that way also, in that case also, in the second case also, we can say that every open ball in open ball of O contains some point of A, and therefore we can say that thus we can can say that it contradicts. We can see that it contradicts the assumption. Which it's a contradiction to the assumption. What is the assumption? And this contradicts the assumption that we have accepted the statement that each non-empty open set in X contains an open set whose closure is disjoint from C. It contains an open set whose closure is disjoint from A. So its closure avoids A, but this situation is not true. This situation, we cannot proceed with this situation, this assumption. We cannot proceed with the truthness of this statement because of the situation we have obtained here. Because of the situation generated here. That this situation, the new situation which we have obtained here, contradicts the assumption that every non-empty open set in X centered at open set in X contains an open set. Every non-empty open set contains an open set whose closure actually avoids the A, and this situation is contradicted, and therefore you have to correct the loosely accepted statement that closure of A is not equal to phi. That means the interior of closure of A is non-empty, and that is wrong. This statement is wrong. This must be corrected. That means interior of closure of A is empty, and that means A is nowhere dense. So when we correct it, that you have to correct it like A is nowhere dense. So this is the end of the proof of the statement. Okay, thank you.